Well, this is not only the first lesson in chapter 14, it's actually the first lesson of two that you're going to be doing today. So even though this is one recording, you're actually going to be watching two recordings today because you'll be doing lessons 1 and 2 of chapter 14 today. There are also two worksheets that go along with each one of these lessons. So when you get done with this lesson, make sure that you jump over to lesson 2 and get through the information there as well. So this whole topic is called thermochemistry, or the chemistry of energy and heat. And so we're going to be walking through this. This lesson is on energy, and lesson 2 is on heat itself. So the build to the essential question here, what's energy? And we're going to look at both potential and kinetic energy and how they're different. We'll talk about chemical potential energy and talk about the heat lost and gained, and then how much energy is absorbed and released by substances as it changes temperature. And so that's what we're going to do. There's a lot of calculation in this chapter, so bust out that calculator because you're going to need that as we go through this lesson and the worksheet together. So some new vocabulary here. You should know most of these terms, or at least heard of them before, maybe with the exception of specific heat, but we'll make sure to define through that. Remember that temperature is a measure of the average kinetic energy of the particles in a sample of matter. In other words, it's how fast they're moving. So higher temperatures have faster moving particles. All right, so the nature of energy. Energy is the ability to do work or produce heat. You should have learned that in middle school. And it exists in two basic forms, potential energy and kinetic energy. So it either has the potential to move or it is moving. And all energy is a transfer between those two phases. So because energy can't be created or destroyed, if something is losing kinetic energy, it's gaining potential energy and vice versa. In chemistry, we look at potential energy in terms of chemical potential energy, the energy that's stored in a substance because of the way it's composed. This energy is stored in the arrangement of the atoms and the strengths of their bonds. So if we look at something like water, in a water molecule, you have the attraction of a pair of electrons. So each bond is a pair of electrons, and that attraction is they're being pulled towards each other, or being pulled towards each of the nuclei in that bond. And so that pulls, like pulling a rubber band, pulls that tight. So there's an attraction there, but at the same time, there's a repulsion from each one where the negative electrons in the oxygen are repelling the negative electrons in the hydrogen, and the positive nuclei in the hydrogen are repelling the positive nuclei in the oxygen. So it's kind of like a spring. The spring is being pulled and compressed, and it's finding a distance at which it's got its least amount of pull or compression. So that's a potential energy scenario. If we were to pull on the hydrogen and oxygen and we were to pull them separate directions and then let them go, it would snap back to its original spot. Just like a spring, if you were to stretch it and let it go, it would snap back. So that is a potential energy. The movement of it snapping, or the movement of us stretching it, is kinetic energy. So in chemistry, potential energy that's within the chemical structure of the molecule can be converted into kinetic energy as it gets as we interact with it. Heat is defined as the energy that is in the process of flowing from a warmer object to a cooler object. That's the definition of heat. In chemistry, energy is transferred most often in the form of heat. So during a chemical reaction, as energy transfers from one substance to another, heat is produced. Now we see it as being generated or created, but it's not. It's just changing form from potential energy, chemical potential energy, to kinetic energy. And so we say something that is hot has a high temperature? Well, if temperature is the average energy of motion, that's kinetic energy. In this discussion, we're going to say that Q is the symbol for heat. So whenever you see a lowercase q, that's what we're talking about. We're talking about it in terms of heat, and the unit that we're going to use is the joule, and that is symbolized with a capital J. When a warmer object loses energy, its temperature decreases. Whatever gains that energy, its temperature increases. In the metric system of units, the amount of energy required to raise the temperature of 1 gram of pure water 1 degree Celsius is called a calorie. So if it's the amount of energy for 1 gram of H2O to increase 1 degree Celsius, that is 1 calorie. That's in the metric system. But in the SI units, which is what we use today in science, the energy, the unit for energy is the joule. 1 joule is 0.2390 calories, and 1 calorie is 4.184 joules. This is a conversion table, so you can see some relationships here. So let's try one. Let's do some conversions here. It says breakfast cereal or orange juice and milk might contain 230 big C calories, so nutritional calories. Express that energy in joules. Well, we don't have a direct conversion from big calories, big C calories, to joules, but we can go through the small c calorie. So we know that 1 calorie is 1,000 little calories. Or we can do it this way. If we follow this table down here, we know it's 1 kilocalorie. And for every 1 kilocalorie, we have 1,000 calories. So we'll call them cal, like this. And for every 1 calorie, we have, let's see, we're going to say for every 0.2390 calories, there we go, we have 1 joule. All right, so these are the conversion factors that we're using here. This factor right here comes from this box here. So there's a couple different ways we could do this, or we could have said 1 calorie here is 4.184 joules. Okay, either way, and now we're using this box to do our conversion. So we get the same answer either way. All right, so to calculate through this, we're going to take 230, we're going to multiply it by 1,000, and then I'm going to multiply it by 4.184, or you could divide it by 0.239 and you'd get the same answer. And for this one, you would get 962,320. In other words, 962,320 joules of energy. If we were to convert that to kilojoules, which is a more common method, we would just divide by 1,000 and we would get 962.32 kilojoules. My pen will right here. All right. Anyway, it's kilojoules there. All right. So go ahead and do some on your own. Do numbers 1 and 2 on your worksheet, which are working through conversions. All right, so the next concept is the idea of specific heat. Specific heat of any substance is the amount of heat required to raise the temperature of 1 gram of that substance by 1 degree Celsius. So some common specific heats are given here. The specific heat equation is given as Q over M times delta T. Okay, so that's the equation used to calculate specific heat. C sub P just means specific heat. That's all that means. Remember, Q is the heat in joules. M is the mass in grams. And delta T is the change in temperature in degrees Celsius. All right, so those are all the units. You can see water out of all of these have one of the largest specific heats, which means it takes more energy to increase the temperature of 1 gram of water by 1 degree Celsius than it does any of these other things. That shouldn't be surprising if you've ever tried to boil pasta. If you have water and you try to boil the water, it takes a long time for that water to get hot because water takes a lot of energy to heat up because it has a high specific heat. When we look at the specific heat equation, this is the equation written in as a computer. I had written it a second ago like this, which is the exact same thing. One thing we need to recognize is that anytime that we have a reaction taking place or a physical or chemical change, we have the surroundings and the system. And we're going to actually have a discussion about that a little later, but we just need to know that the heat always transfers between the thing that we're looking at and everything else. So we call it the system and the surroundings. The system and the surroundings are negative of each other. However much energy one of them loses, the other one gains. Most of the time, we're going to have problems that look something like this. I have water here, H2O, right? And in my H2O, I'm going to take a block of metal that's hot. So it's radiating out heat, and I drop it in the water. Well, the temperature of the metal decreases, and the temperature of the water increases. The heat, Q, the number of joules in each one of these cases are the same, but negative, because however much heat the hot block loses into the water gains. They don't lose the same amount of temperature or gain the same amount of temperature because they might be different masses and different amounts, but the overall amount of heat, Q, is the same but opposite, negative of one another. Well, the specific heat equation can be manipulated by multiplying both sides by M and delta T. So we basically get C sub P times M times delta T equals Q. So we'll say Q equals M times C times delta T. And that's the equation given up here, the one that you'll find in your book. So let's calculate through one so you can see how these are done, and then you can try some on your own. It says in the construction of bridges and skyscrapers, gaps must be left in the steel beams to allow for the expansion and contraction of metal due to heating and cooling. The temperature of a sample of iron with a mass of 10.0 grams changed from 50.4 degrees Celsius to 25.0 degrees Celsius. With the release, it released 114 joules. What's the specific heat of the iron? So we're going to look at this. We're going to say, well, specific heat, C sub P, is equal to Q over M times delta T. So let's go ahead and plug in here. C sub P equals 114 joules, but it released that 114 joules. So that means that it was negative. It gave it up. It didn't gain. If it gained, it would be positive. So we have a release of a negative 114 joules. It's 10 grams of metal times the final minus the initial temperature. This is the final. this is the initial, so it's 25.0 minus 50.4. And we take 25.0 minus 50.4, and we get negative 25.4. All right, so now we solve through. We're going to take negative 114, and we're going to divide it by negative 254. And so we get the specific heat of the metal is 0.449 joules per gram per degree Celsius. Okay, so that's my answer right there. So again, specific heat, Q is in joules, M is grams, and delta T is the temperature final minus the temperature initial. And so that's how I solved that one. So go ahead and go to your worksheet and do numbers 3 through 5 on your own. All right, well that ends the lesson 1 video, and you should have completed the lesson 1 worksheet. So now that you're done with that, go ahead and jump on over to lesson 2.